Let's start our lecture number 12, and we will continue talking about the method of images now. Previous class we spoke about method of images for planar boundary, the charge distribution close to this boundary. Now we have the method of images for spherical boundaries. The situation is going to be a little bit different in terms of the magnitude of the charge of the method of the image charge. So, in summary, we're going to talk about the method of image for spherical boundaries and also for cylindrical boundaries. I'll make a parenthesis and do also for cylindrical boundaries. This is not explored in Jackson's book, but I mean, in this class notes you have the recipe to use it, for instance, to calculate capacitance per unit length of coaxial transmission lines or parallel wire transmission lines. So that can be obtained by this method of images. And at the end we are going to construct the Green's function for spherical boundaries for problems within in regions enclosed by spherical shells with prescribed boundary conditions. Reference chapter 2 of Jackson, and also we have our chapter 3 of the ebook. I didn't write here, but we have that also in chapter 3 of the ebook. So let me just put here ebook, put in black, ebook chapter 3. Okay, the book, of course, is the book in our web page, is our own ebook by me, right? Now we have two situations that we might explore. We might solve the problem outside of a sphere. Let's start with the grounded sphere. We can solve the problem, let's call this the exterior problem. Then after we solve this one, we are going to see how to use the results to calculate the solution for the interior problem. Well, we check on the possibility of equilibrating the potential with the image charge located inside of the sphere. In this case, that's the original problem, right? We have a charge, a grounded sphere. We could place the image charge anywhere inside of the sphere, but I mean, it makes more sense that we put the charge on the same axis that is defined by the origin and the location of the charge. So we have that axis. So we're going to place now an image charge Q prime located at coordinate C, a distance C from the origin. The original charge has a distance B, and A is the radius of this sphere, okay, right here. So B is original charge location, C is the image charge location. So our job is to determine Q prime and C, okay. Let's do in vector notation. Charge image original charges at B AZ. Let's pass the z-axis on the charge, and Q prime is going to be at CAZ. So the potential for x larger than A, magnitude of x, is the sum of the simple sum of potentials, right? And we are going to set the potential equals 0 on the sphere. We have again, before doing anything, just notice that this is a positive definite quantity. This is also an absolutely positive quantity. So sine of those two quantities have to be opposite. So Q prime has to have a sign that is opposed to that of Q. So if we set the potential size of X equals to A equals to 0, then playing around, just multiplying, cross multiplying here, and moving one of the terms to the other side. Okay, so we have that calculation. Magnitude of the difference between two vectors is the square of the first, square of the second, and 2 times the dot product. Then when we do that, so if we apply that, for instance, we just do square here. We do Q square, right? Magnitude X minus BAZ square. I lost the sign, right? Q prime square, but the sign, we know that Q prime is negative, so we have to keep track of that. X minus C, is this right? No, it's not right. Q square X minus C equals to Q X minus B, AZ magnitude square. Then we expand, right? So we're going to have Q square, then we're going to have magnitude of X equals to A, right? So it's going to be A square plus C square minus 2 X dot AZ, which is the magnitude of X, magnitude of AZ, cosine of the angle, which is theta, is the polar angle. So this is going to be 2AC cosine theta equals to Q prime square, same thing, A square plus B square minus 2AB cosine theta. Then we rearrange this, right? Am I doing right here? I think so. Yeah. So when we rearrange, we put a constant term, a group constant term, and the coefficient of cosine theta. We're going to have Q square A square plus C square minus Q prime square A square plus B square. There's one coefficient, which is this one with that one, right? The second one is this and this. Group it together. So it's going to be minus 2A. Then we have Q2C. Then this one minus Q prime square B times cosine theta. Then this is 0 for any value of theta in the interval 0 to pi, right? So we have here one relationship is going to be this one. Q2C equals to Q2B to set, a function of theta, right? Something like A plus B cosine theta. We want to be 0 for all theta in the interval from 0 to pi, so A has to be set equal 0 and B 2. So A is this coefficient here, and B is this one. I'm doing B equals 0 right now. Sorry. Q2C equals Q prime square B. So Q prime square equals to Q square C over B. Then we plug that in here, right? And we do some algebra. That's for you. then we find this result. So we have C, the distance of the image charge inside of the sphere, is the A squared over B. Because B is larger than A, C is smaller than A, right? And Q prime, already with the sign incorporated, is a fraction of Q. It's not equal to Q. So in the planar boundary, the image charge was equal to the charge magnitude. Now the image charge has a smaller magnitude than the charge. So and the ratio is A divided by B. So A is smaller than B. So the image charge is smaller than Q in magnitude, right? So just notice, let me write down here the location. And value minus IA over B minus B over A minus A over B times Q. So if you look at this, as B grows to infinity, the image goes, I mean, if the original charge is far away, right? So the charge image goes to the center of the sphere, right? And also, the magnitude is going to 0, right? Because B goes to infinity. In addition, if B goes close to the sphere, very close, right? So we're going to have almost a planar surface now. So if B goes, C goes to A as well, right? So we're going to have the charge and image charge very close to the radius of the sphere. And here you see that A over B goes to 1. So Q prime is going to be almost equals to, in magnitude, equals to the charge. So it's almost like a flat surface, right? You have a surface like this. So it's so close that you have an approximation of a flat boundary, okay? So, first question, what is the induced charge? So just notice this important hint here, right? The image made for a spherical surface, A is the geometric mean of A and B, so of B and C. So B times C equals to A squared, or A equals root square of BC. A is geometric mean of between B and C. That's a nice hint, so we don't forget that. So what is the induced charge, right? So we just use Gauss's law to determine that. The question is, what is the flux that goes through the sphere? Right? What's the flux that crosses this surface? Because all field lines that cross this red surface here, they will end up on the sphere. So it means that the integral of the flux density vector gives the total charge, right? Well, by construction, we see that the Gauss's law, the flux that gets, sorry about that. The flux that enter the surface, it ends, all the field lines end in the image charge. So the induced charge is exactly equals to Q prime right? Which is minus A over B times Q. So the induced charge is equals to the image charge, right? So that solves the problem. We have you have the potential outside of the sphere in a potential that has a singularity on the point charge outside of the sphere. So how do we solve the interior problem? In other words, given the sphere, right? Now we have, instead of having the charge outside, now I have a charge inside. I have a grounded sphere here. That's the center. Then we have a charge Q inside, right? So, I mean, if we put the charge inside, located at a, oh wait, what is it? Well, at a distance B, right, from the center, the image charge is going to be outside at a distance C equals to A2 A squared over B, right? And also the same thing, the induced charge equals to minus A over B times Q, right? Same result. Now the image charge is outside, right? Because this is B is smaller than A, so the location is outside, and the image charge has a magnitude which is larger because this ratio here is larger than 1. The magnitude is larger than Q, right? What else we have here? Well, what is the induced charge in the inner surface of the sphere? Let me put some thickness here. I hope I can make a round. Yeah. So what's the induced charge? Well, calculate Gauss's law, right? Pick any surface that encloses charge Q, right? Put it like this. Now all the field lines that leave Q, they end on the inner surface of the sphere, right? So by Gauss's law, the flux that crosses this closed surface is equals to Q. So it means that the induced charge is minus Q inside of the sphere. So I ask you, what's the charge outside of the sphere? Well, outside in this problem, the potential here is grounded. Potential at infinity, let's assume is 0, 2. So solution outside is potential equals 0. Field outside is 0. Flux density is 0. Surface charge density on the outer surface here is equal to 0. No charge outside. All the charge is inside, right? Nothing is outside. There's no E field outside. All the charge is here. On the inner surface, remember the problem that I was exploring in next class, right? So you have charge here, let's say they are negative, and there's nothing here on the other surface. So we have alternative situation that we like to talk about. So we can easily solve it, I mean, by using superposition. Suppose we have, for instance, charge outside and you have a sphere at potential V. How do we solve it? Well, we solve two different problems. First, we solve a problem in which the potential is that due to a point charge and a grounded sphere. That's called the solution phi 1. Then we have a separate problem in which there is no point charge, right? And the potential in the surface is at the potential V. So let's see how this works. We solve the first problem. Problem 1 gives me a solution phi 1. Problem 2 gives me a solution phi 2. Phi 1 has a singularity due to a point charge, right? This one doesn't have, outside, I'm talking about outside, no singularity, right? So what is the Laplacian of phi 1 plus phi 2? Equals to Laplacian of phi 1 plus Laplacian of phi 2. Well, Laplacian of phi 2 outside is 0 because there's no singularity, there's no charge density. And Laplacian of phi 1 is minus the density of the point charge, which is Q delta x minus b az, right? So that's the Laplacian of this combined solution here. Okay? What else? What is the solution at magnitude of x equals to a? Well, it's going to be phi 1 at magnitude of x equals to a plus phi 2. Well, this one is grounded. The solution 1 is the one we solved, is 0. And this one, by definition, is V, right? So we have the sum satisfies boundary conditions, and the sum satisfies Poisson's equation. So by uniqueness, that's the solution, right? So that's how we do it. Break into two solutions. So the solution 1 is the one we just solved, is the potential of a point charge outside of grounded sphere. We have a solution for that. The additional solution is that due to a sphere with a potential V, which is going to be given by this term here, right? Same thing if we have a charged sphere now, right? Well, a charged sphere means that we have a constant potential. It's the same problem, right? We just have to break the charge onto a part that is no uniform distribution induced by Q. So there's one part here which is Q prime, which is a charge that is on the sphere due to Q, due to the presence of Q. The remaining part is going to be uniformly distributed, right? Because, and this one here the potential is 0 when you put just, when you solve this problem here, you have a charge which is Q prime, right, induced on the surface. And the remaining part is going to be that amount of charge that gives a constant potential on the sphere. And that constant potential on the sphere means outside, right? Constant potential V on the sphere means, without any point charge outside, means that we have uniform distribution. So the remaining charge, which is this one here, distributes uniformly. So the solution is that, potential of a point charge near a grounded sphere plus potential of a uniform distribution Q minus Q image, right? So so the first solution is phi 1, is that the one that we solved. I mean, point charge near grounded sphere. Second solution is uniform distribution Q minus Q image. Q image is Q A over B. So the potential for uniform distribution is given by this. Now there's some mistake here. 4 pi epsilon 0 r. Okay, I forgot that. So another mistake. Okay. I have to fix in the notes, in the class notes. I might fix that and upload it again, but I might forget. So let's see how we do. So that's the solution. So you solve all classes of problems by doing this. Well, let's calculate the force between point charge and charged sphere. That's an interesting problem, right? We have a charged sphere, let's say. Well, then we have the charge, right? We just mentioned that this problem can be solved by separating into two problems. One is the grounded sphere with a point charge, and the other one, uniform distribution of charge given by Q minus Q prime on the surface uniformly distributed. So the problem is equivalent to a point charge Q, a distance B from the origin. So here is the origin, okay? This is the location of the charge. So the image is located at a distance C, which is here. And the remaining charge is the one that distributes uniformly, but a uniform distribution is equivalent to a charge at the center. So all we have to do is a force, but I mean, once you calculate the force on Q, it's going to be the force of Q prime on Q plus the force of Q minus Q prime on Q. So if you calculate that, okay, there's some you know, it's not difficult to calculate, it's very simple. But it's important to consider that this force is the force that points toward the z-axis, along the z-axis. So if the force is positive, you have a repulsion. If the force is negative, you have attraction. And we are going to analyze force between charged sphere and the point charge, even if they have the same sign or opposite signs, right? So we're going to explore the situation. So I'm going to leave this algebra here, but I mean, we calculate the force and express the results in this formula here. I'm going to explain you. I ask you to try to cast the formula like this. Go through the notes and do the calculation. Let's see what the parameters are. Alpha is defined by Q over Q. So the sphere has charge Q, and the point charge has lower Q. This is called this alpha parameter. Okay, so there's one parameter. So I have the ratio between the charges. If this number is positive, the charges have the same sign. This number is negative, the charge has different signs. The other parameter that appears here is beta. So beta here is the ratio B over A. So I have the location of the point charge, sphere of radius A, B over A equals 1. You have the point charge very close to the surface. So this is going to be called beta. So we're going to see the effect of the force as we approach or as we go away, move away the charge from the sphere. And we're going to see how that depends, how the sign of the force depends on those two parameters. So there's a point in which the charge changes sign, okay? So let's assume that both charges have the same sign. So let's consider the situation, which is the most interesting one, in which alpha is larger than 0, right? So that means Q, capital Q and lower, uppercase Q and lowercase q have the same sign. So there is a point in which the force changes sign. So it's when this parameter changes sign, we can calculate, we have an approximate result for that. I mean, the ratio of the location of the charge relative to the radius is given by this parameter here, okay? So it means that there's a point, a certain threshold for a given, for a given ratio between the sphere, the charge of the sphere, and the point charge, the point charge magnitude, in which we have, very close to the surface, 1 plus a small number plus a factor here, right? So maybe I can show you here. Maybe it's easy to show here, okay? So here are some plots of the force. So attractive force happens in this region here, okay? Attraction is everywhere where the force is negative, and repulsion is when the force is positive, okay? So so you see that for alpha equals to 4, what does it mean? Let's see. Q equals to 4 times Q, right? So charges have the same thing. As we approach, and alpha is this z-axis here. This is alpha equals 3 alpha. I'm sorry. This is beta, right? This is beta, which is the distance is shown here, right? Beta. So as the distance starts to decrease, if you approach the charge very close to the surface, even if the charge has same sign, right, there's a point in which the force changes sign, and the repulsive force starts to be an attractive force, right? So I have, for instance, a positive point charge and a positively charged sphere. If you approach very much the charge for this radio, for instance, capital Q equals 4 Q. When you go to this value, this is 1, right? Here is 1. So here in this point, A equals to B, okay? So there's a point at 1.2 in this case, 1.2, B equals to 1.2A, in which the force is thought to be attractive, right? So it means that you have a charged sphere with a charge larger than 0, then you have a point charge, and we are going to have attraction. Why is that happens? Why that happens? Because the charge induces such a high degree of non-uniform distribution. It's just close to the point, you have a very high density of charges, induced charge. Let's put the negative sign here, sorry. Put blue there. So I have a very strong attraction. So that explains, let's say qualitatively, the work function of metals. If you have a metal that is charged with charge Q, and we try to extract a small part of that charge to remove that from the metal, the metal still remains with the same charge, right? So if you want to, let's say Q is smaller than 0, you want to remove 1 electron from the surface of the metal. Well, it's very difficult to remove because you have an attraction between those two charges. because of that. I mean, because of this non-uniform distribution of charge induced on the surface of the sphere in this case, and that's why we have this work function of metals. We need some energy to knock out some charge of the sphere. Okay. Let's make an example. I mean, you can solve this problem. We did that before using legendary polynomials. Now let's use method of images. We assume that we have, we have a uniform field, a region of uniform field. Then we place a sphere. Sorry, I think it's rounder. Not too round like this. Okay. Then we put a sphere in this uniform region of uniform field, conducting sphere. So what's going to happen is that we are going to distort, right, the field. The field is going to, we are going to induce charges on the sphere. I mean, the field has to bend, so it has to end orthogonally to the surface. So we're going to have something like this, something like that, right? So we're going to have this type of situation, and then you're going to have something like that. So this is a problem to be solved. So the problem can be modeled assuming that we have 2 point charge very far away. Like this. Charge that's minus capital Q plus capital Q. Let's say that they are 2L distance. So what happens? So they are so far away that the field at the center of the sphere, let's say, the sphere is so small, right? When you have those charges so far away, that the field at z equals 0, let's say this z-axis, this is minus q, this is q. The E field here is the sum of two E fields, one due to the positive charge and one due to the negative charge. So the field is going to be q over 4 pi epsilon 0, let's call this L, okay? So L square, approximately, AZ. And the other field, due to the other charge, also is the same thing. It's Q 4 pi epsilon 0 L square AZ, which is going to be Q over 2 pi epsilon 0 L square AZ. Let's consider L much larger than the radius of the sphere. Okay, that's the approximation, okay? So the field is given by E0 is a constant field in the absence of the sphere, with E0 known, which is Q over 2 pi epsilon 0 L square, okay? So what happens? I mean, if we use the method of images, if we go back to the original problem, right? We have a charge. It's going to have another charge, so we can replace the grounded sphere. This is grounded, right? We can put an image charge Q1 due to that charge. So with this Q1 and minus Q, equilibrate the potential on the sphere. So the potential is 0. But to equilibrate the other one, it has to put another image Q2, right? On the left, right? So equilibrate the potential. So the values are known. Q1 equals to radius of the sphere is A over L times capital Q, and Q2 is minus that. So what do we have? We have an E field that's uniform plus a dipole. Okay? So the potential outside is like that due to a point dipole. So the potential, let's say the field is zero, original field is 0 AZ. That gives me a potential function of the form minus E0 Z, because gradient of phi equals to E0 AZ. So one potential is going to have one term, which is the original applied field, plus a distortion due to a dipole, right, a point dipole at the origin. Okay, this dipole is the result of two charges. Let me increase the distance here. Minus and plus. We have a dipole. The distance here, if we look at, this is the location of the positive charge, A2 over L. The negative charge has the same distance. So we have here a dipole. The distance here is 2a squared over L. So it means that we have a dipole moment equals to this charge here, which is A over L times Q, that's the charge, the positive charge is this one, times the distance, which is 2, A2 over L, times AZ. So we have a dipole which is 2qa squared over L squared AZ. So the potential of this dipole, right, which is the result of the presence of the sphere, is given by, so the total potential is the potential due to the uniform field, but plus the potential of this, let's say phi d is the dipole. The potential of the dipole, we did that before. Look, we have a point dipole, right? We have a sphere which has a radius much larger than the size of the dipole. So we can use the asymptotic approximation. So the potential is equals to P dot AR divided by 4 pi epsilon 0 R squared. So the additional potential due to the image charges is this phi d. So we have the potential due to the point charges far away from the sphere that gives a uniform field, and the potential due to the dipole. So let's calculate phi d equals to, where is it? Right here, right? So we're going to have 2q a squared over L squared AZ dot AR divided by 4 pi epsilon 0 R squared. Now let's recall what's the E field here. Is 0. We just calculated the E0. I'm sorry. Here. We have the E0 somewhere here. That's the E0. Let's move that to there. Put it here somewhere. Right there. Right? So you see here, this gives me, you see a square, q divided by 2 pi. I think I missed, I'm sorry. This q is a capital Q. Sorry about that. Right? This is a capital Q2 here. So we have, by looking at this, we can replace Q divided by 2 pi epsilon 0 L squared by E0. So this is going to be, the 2 here cancels this 4. We're going to have E0 times a square, this dot product is cosine theta divided by r squared. So that's the additional potential, okay? So let's see what happens. That's the potential, the additional potential due to the sphere, right? Otherwise, we have just this solution here. So the potential is that minus E0 z, or this is equals to r cosine theta, plus the dipole field, which is E0 A2 cosine theta divided by r squared. Let's write it again. Let's do it minus E0 I think it's right, plus that's the result, and I can rewrite like this. Let's see how did I hope it's, yeah. It's going to be E0 minus r plus a square over r square, right? Cosine theta. So you can see that this is exactly the solution. So this the, r L, and here 1 over r L plus 1. This is P1 of cosine theta. There's the first term in the series, the L equals 1 term. The solution has the L equals 1 term outside of the sphere, right? So let me just show you here. That's the solution, right? So this gives the uniform field. This gives the dipole field. Also, you can calculate the E field by calculating the two components. E field is going to have two components, ER and E theta, because potential depends on R and on theta, and we can calculate those, right? Just go to E equals to minus AR d phi dr. You have the radial component minus a theta d phi d theta, right? So in fact, what you have is the uniform field, but plus the dipole field. You have this function here, right? And you can calculate the field at r equals a, and you're going to have a function of that. I mean, it shows here that you have a surface distance of charge, which is the normal component of D, which resembles the normal component of E at r equals a. The normal component is right here, right? At a equals r, this gives 3 times cosine theta. So that's why we have that. And the maximum charge density is 3 times this number. So it enhanced, the charge is pulled, to the, have a large charge density, have a field like this, uniform like that. The charge accumulates on these regions here, and they get 0 here, right? And they are more intense on the poles, let's say. Okay. I'm going to outline the method of image for cylindrical boundaries. We are not going to do the, all the algebra that is in the class notes. I mean, you do more detailed passages. I'm just going to outline how to obtain the results. So let's see this problem here. We have a charged line, right? I mean, we're looking at the XY plane. We have a cylindrical surface here. And we have, next to it, we have a parallel straight line going from minus infinity to plus infinity in the z-axis. This problem is instructive to determine the capacitance of coaxial lines of any pair of coaxial cylindrical surfaces or parallel cylindrical surfaces, or one inside of the other at different locations, different position of the center. You can calculate the capacitance of all of this, but just solving this problem. Again, let's place the charged line, straight charged line, at with a density of lambda at a distance b, okay, on the x-axis, and the image is going to be lambda prime, charge density, linear density of charge at location C. Same terminology as the spherical surface. Well, we already did this work. I mean, a charged line has a potential, right? Which we calculated before, minus lambda logarithm of r plus another constant, let's say lambda log of a. So it means that r equals a, the potential is 0. So if I have a charged line in the grounded surface, okay, at r equals a, you have this solution here. In fact, yeah, so the field here, because minus gradient of phi would give in fact, I mean, that has some constants, right? So that's lambda divided by 2 pi epsilon 0. Here too. So when you have that, the field is going to be lambda over 2 pi epsilon 0 r a r. Okay? So that's a solution when we establish that a reference to the potential at a surface, r equals a. In this situation, we want to establish, I mean, when you have a charged line outside, we can try to to balance the potential at the surface r equals a. By trying a solution that is a combination of the potential of a charged line at location at distance b from the origin. I mean, the r in the case I just showed changes from the magnitude of the difference vector, so it means in fact, what's here is the distance, right? Is this magnitude here of this r prime here, okay? So that is this vector x rar minus bax. So that gives me r prime, which is this number here, okay? So I'm going to attempt to use that potential, which is the potential of charged line, right? That's going to be a constant potential somewhere, okay, we are going to add the potential of the image line, which is located at C. So that's a possible solution to the problem. We are going to impose that this solution gives V volts on the surface, okay? Let's do that V different than 0. If we want to ground that, we're going to subtract V volts, then have a 0 potential. Okay, then potential at some other places would be changed, right? But we can start with the potential V. So what we are going to do is just to equilibrate at x equals to AAR, the potential equals to V. We just replace that and impose that condition. So here, I mean, the way to do it, you see that when we impose the potential at, let me just write separately here. The solution that we propose for this problem equals to minus lambda, that's the original charged line, logarithm of x, which RAR minus BAX. Then we have an image. We didn't put any sign in the image line, okay? Which has a similar structure, log of RAR minus CAX. So what we're going to do is that when RAR, or in the other words, when R equals to A, right? So that's the radius of the cylinder. We want to impose that when RAR magnitude equals to A, then we have a potential which is V. So V equals to minus lambda over 2 pi epsilon 0 logarithm of, R equals to A, so it's going to be AAR minus BAX, sorry, plus lambda prime minus, minus CAX, okay? So here we can calculate, you see, let's just draw here the surface. So we're going to have the angle between AR and AX. When this angle changes, this is the angle phi. You see that this function, this is a function of phi. That's all we have to do, okay? And what the way to determine lambda prime and its location is to impose that this function is constant. This function is independent of phi. Okay, so how do we do that? Well, you see that's complicated because we have the logarithm here, right? 2. So what we do is to impose that the derivative of this function, let's call this fictitious function, let's call it h of phi, equals to this. H of phi. We impose that h of phi has a 0 derivative. That's the technique that we employ here. So when you calculate the derivative, the logarithm, derivative of log, right? let's call it, the magnitude equals to 1 over magnitude d d phi of the magnitude. That's how we do it. So when you do that, we obtain an equation of the form, just show you. I mean, then I'm going to jump 2 or 3 slides here. We get something like this. Yeah, when you do that, just do that derivation. Let me see what I have here. Okay, here, I think I found it. So we have this condition. After you do the derivatives, then I have this thing here, which is a constant after you calculate the derivative, plus a term times cosine. So as always, I mean, this is a function of phi, right? Once you make it 0 for any phi between 0 and 2 pi, we just set this equals to 0, and this equals to 0. Immediately we see that lambda prime has to be minus lambda. And if we play around with this thing here, we find again the same result. A is a geometric mean between B and C. And lambda prime equals to minus lambda. So then we solve the problem, right? We have a solution. We found the image charge, then we can calculate the potential. The potential is going to be simply the solution here, right? The potential is that the original charge minus lambda 2 pi epsilon 0 log of RAR. I'm going to leave like this, minus BAX plus, because lambda prime is minus lambda, plus lambda divided by 2 pi epsilon 0 log of RAR. Here you're going to have minus a square over BAX. So that's the solution, right? Solution outside of the cylinder in that region, in this region here. Right, it has a singularity on the charged line, and the potential is V on this surface. Okay. Okay, so this allows us to determine solutions of the potential distribution between two cylinders, okay? Like in this example here. Let me see, where is it? Here, right? So in this problem here, in fact, the original problem, we have this cylinder at potential V, have this other cylinder at potential minus V. Well, this surface is one equipotential at potential equals 0. Then we claim that we can simulate these potentials. We can solve this problem by calculate the potential due to two charged lines, lambda and minus lambda, right? Why is that? Well, because we just did that. I mean, one charged line can equilibrate the potential on one surface, and another charged line can equilibrate the potential on the other surface. So we have to find what are the equipotentials for two charged lines, fictitious charged lines. So the problem is this, I mean, given, right? I mean, this problem is like this. The original problem is this. We have two conducting cylinders. All we know is the distance between centers. We have this information here. I have the location. I have D, right? I have also the radius A of each cylinder. Could be different radii, okay? I'll leave it to you to solve that one. And also I have the potential V and minus V. So given this situation, what is the capacitance per unit length of this structure? Well, if we find equivalent charged lines that give a constant potential at those two surfaces, then we solve the problem, right? You see, I mean, we solved this problem before. Here we have, for instance, just to show how equivalent this is to the image method, this is the location of one charged line, which is at B. So the image is going to be located at C, right? Equals to A squared over B, right? So the problem is comprises determining those things. I mean, so given D, right, A and V, we have to determine what is the density lambda, okay, and the H parameter, which is this parameter here, the distance between the two charged lines, H, okay. So we have to determine lambda and H. You see that this distance here is by symmetry, right? This is A squared over B. So I have B plus A squared over B equals to D is one first relationship. This gives me an equation, B squared minus D times B plus A squared equals 0. Is a second degree equation. I can determine B. Here's the solution. The solution that makes sense is this one here. So if we do some calculation, there's some 2 pages to do that. I'll leave that calculation to you. Then we find that the potential can be reaching, I mean the charge density and the potential, or vice versa. I mean you have a relationship between lambda, the charge density of this fictitious charge line, and the potential V of one of the electrodes, and entirely written in terms of the parameters of the problem. The separation between centers the radius of the cylinder. When you have that, I can rearrange that and write in this form. Okay, have some algebra here too to do. This can be cast in this form here. Okay. So here, I mean, the capacitance per unit length is the charge density, the linear charge density, which is the same charge density in the corresponding cylinder, divided by potential difference, which is 2 times V. If I do that, lambda divided by 2V, you have the capacitance per unit length of this pair of conducting cylinders. Okay, so I'm not going to explore much of this calculation because it takes a long time. I'll leave that for you but just to illustrate, that's one problem that is solved by the method of images. Okay, let's conclude the class. Let's look into the method of the Green's function for spherical surfaces. Right? I mean, once we have solved the method of image, so 1 point charge next to a grounded surface, we can find the Green's function for the Dirichlet boundary value problem in the domain between a spherical surface, right? The exterior problem, for instance, can be the interior problem as well, but I mean, I can solve, for instance, the exterior problem of the potential distribution for any charge density outside with the potential given on the surface. I'm sorry, it's not the ground surface, but I mean, giving a charge density and the imposition of the potential as a function of theta on the surface, I can solve the potential outside, for instance, given that the potential for the R going to infinity equals to 0. So this is a boundary value problem of Dirichlet, right? How do we do that? Well, we find the Green function, which is the solution of a potential of a point charge of 4 pi epsilon located at the point next to a grounded sphere, right? So the problem I have at stake is this one, right? I have a point charge 4 pi epsilon located at x prime, and we find the solution to this problem at point x. So when you have a 4 pi epsilon charge, the Laplacian of the solution is the charge over epsilon times the delta function, which is 4 pi delta. So that's the Green function, right? The solution to this problem is the Green function. So for Dirichlet, that's GD, and GD on the surface of the sphere is 0. And GD at R going to infinity is also 0. Let's call this versor here U prime, which is x prime divided by the magnitude. The angle between x and x prime equals to gamma. So we already solved the problem, right? Just a matter of putting the 4 pi epsilon in place of q. Then we have the Green function for the sphere for the Dirichlet boundary value problem. Now, looking at the geometry here, the construction, gamma is the angle between x and x prime, okay? So we have to calculate those magnitudes, square the first, square the second, 2 times the dot product. Angle between x and x prime is gamma, so we have cosine of gamma. X minus x 2 prime. 2 prime is the location of the image charge, right? And then you see, I mean, the image charge, sorry, is located, I'm not showing there, but I mean the image charge, do it separately here. So if the charge is at x prime, right, and x prime equals to r prime times u prime is a versor, the image charge is located at a squared over r u prime. So x minus x2 prime, you see that x dot u prime equals to, or in other words, let's call that u equals to x over magnitude of x, which is the radial vector, equals to ar. So because x prime is along u prime and x2 prime also, this is going to be, this square is going to be x squared plus x2 prime square minus 2x x prime, right? x2 prime, sorry, equals r squared plus square of this number here, a4 over, this is r prime, sorry, r prime square minus 2 r a square over r prime u prime u dot u prime, which is cosine of gamma. That's the second factor in the green function, right? This one here. So the green function is going to be this to minus 1/2 minus this to minus 1/2. So we have the green function, and also we need to calculate the normal derivative of the green function outwards of the region of the domain on the sphere. So outwards the domain is inward to the inner part of the sphere, right? So it's going to be minus dg dr prime at r prime equals a. So the other task is to calculate this derivative given this function of r prime. And after we calculate the derivative, we set r prime equals a. Then we have this messy calculation here, right? All this thing here. You do that. Then we have finally the term that goes to the surface integral, which is this one here. Okay. Recall that cosine gamma, if we didn't show that yet, is given by this expression in terms of the polar angle and azimuthal angle of each of the vectors involved. Okay. It's easy to calculate using the dot product. So the solution to this general boundary value problem, this Dirichlet boundary value problem, equals to can be cast in this form here. I mean, I have to increase because so many terms. So I have the density, right? Green function here. And the surface integral that involves the specification of the potential on the surface, which is a function of theta, an arbitrary function, okay? So we have that, and that surface integral, you see the solid angle is right here. This thing here is d omega prime, right? So recall that if the surface is grounded, so this term goes away, right? Otherwise, we have to use it. So one example is to determine, for instance, the potential on the z-axis. If we have a loop, right, a charged loop, circular charged line around a grounded sphere. So we can solve the problem easily on the z-axis if we want. And we can use the technique of finding the solution if we know the solution in a subdomain, which is on the z-axis. We derived that before. So we can find the solution on the z-axis, then we can expand the solution as power series, then multiply each power by the corresponding Legendre polynomial. In this problem, we have azimuthal symmetry. So that's the procedure here, right? We have the density of this charged line here can be cast in this form here in terms of delta functions. Okay, the location is theta prime equals pi over 2, and the location of the spherical distance is r equals b. B is the radius of this charged line. So that's the representation of this charged loop in spherical coordinates. Let's check. Let's check if that's correct, right? Charge density rho equals to lambda divided by sine theta prime delta of, I think there's an R, R prime sine theta prime, delta of theta prime minus pi over 2, delta of R prime minus B. B is the radius of the loop. If I integrate this in the whole space, phi goes from 0 to 2 pi, right? Theta goes from 0 to pi, and R goes from 0 to infinity, times this delta function lambda over R prime sine theta prime, delta theta prime minus pi over 2, delta R prime minus B, so here we're going to have 2 pi lambda r squared divided by r equals to r. Delta function is going to be at r equals b, so it's going to be b here, right? Sine theta cancels. So integral delta function on the theta domain is going to be 1. So that's it. Goes to the charge of the charged line. So the density is Q divided by the perimeter. It's correct, right? So that's how we write the density. Then if we apply the expression, which is right here, right? We're going to use that density right here. Also, this term goes to 0 because the potential is grounded. And how also here we're going to use R equals to Z, okay? So so theta equals to 0, and theta prime equals to pi over 2. If you look at cosine gamma when you calculate, so this is 0, cosine gamma, this is wrong here, cosine theta prime. Because cosine theta prime is 0, cosine gamma equals 0. For theta equals pi over 2, and theta prime, for theta prime equals pi over 2, and for theta equals 0, which is z-axis, right? So if we do that, we have this integral, okay, just putting all the, the solid angles here, r squared dr, 1 over r sine theta, that's density function. This is cosine gamma is 0, so this term here goes away, right? And r prime is going to be equals to b, just recall that, okay? So when we do that, we're going to end up with r z squared plus b squared because it's the axis, right? And that's the other term here. So if we look at that, you're going to notice that it's the potential of a simple, right? We're going to have here, the problem is equivalent to that of a charged line and the image charged line. B and C, right? You have two concentric charged lines. It's very easy to calculate the potential on the z-axis. That's what we did. And the result is going to give this result here. If you look at this, I'm going to do the calculation without using Green's function, right? So this is the result we get, correct? Let's check. The potential of the charged line of radius b equals to lambda divided by 4 pi epsilon 0 z squared plus b squared to 1/2, right? It's not lambda, it's q, I'm sorry. It's q. It's the charge of the q over 4 pi epsilon 0 distance. It's as if all the charge was in the same points. This is equals to lambda times 2 pi b, so the potential of the charged line equals to lambda b over 2 epsilon 0 z squared plus b squared, which is as we have in our result here. That's the first term here, right? Lambda b over 2 epsilon, right? The image charged line, the potential is going to be q prime, right? Q prime divided by 4 pi epsilon 0 z squared plus c squared to 1/2. Q prime equals to minus a over b times q divided by 4 pi epsilon 0 z squared plus c squared. C squared is c equals to a squared over b, so a squared over b squared to 1/2. So this is going to be minus a over b, q equals to lambda times 2 pi b, 4 pi epsilon 0, z squared plus a squared, a to the 4th power divided by b squared, to 1/2. So we have here 2, right? Minus a lambda a divided by 2, then we have 1 over, then we're going to have a b here. This b squared goes up. It's going to be b squared z squared plus a fourth to 1/2. That's the second term. Equals to minus lambda b. I missed an epsilon 0 here. divided by 2 epsilon 0 or epsilon depending on the medium. So we're going to have A divided by B squared z squared plus A fourth 1/2. So that's the second potential, the potential of the image charge. So that's the result we got, right? We have lambda B divided by z squared plus B squared, which is the first one, right? The second potential, second contribution is lambda B divided by 2 epsilon 0, A divided by that. This is right here. Correct, right? So what happens here? I mean, we have just that problem. We have a charge. If you pick an angle here, this is the arc of the image charge. This is the arc of the real charge. So the amount of charge in this region here is lambda times B delta phi. Let's say that this angle is delta phi. And the image charge is lambda prime times C delta phi. So these amounts, the image charge, lambda prime, C delta phi, equals to minus A over B times lambda B delta phi, right? So we can cut those things here, cut off. So it means that lambda prime, the charge density of the image charge, equals to minus A over C times lambda, but C equals to A squared over B, so equals to minus B over A times lambda, right? That's how it is. That's what we got, which is the same result. It would give the same result as we obtained here, right? So I believe that we are at the end of our lecture, and I hope to see you next time. Bye-bye.